Oh, hi friends. I'm not here to play table tennis. I'm going to use this ball and my table tennis racket to teach you the valence bond theory. You may ask how? Because remember, the s orbital is spherical in shape. And this table tennis racket is going to be our p orbital. And we are going to be seeing the overlapping of orbitals, which is what the valence bond theory talks about in this video in a very simple and practical way. And I promise to make the concepts crystal clear to you. So are you guys ready to begin the journey on valence bond theory with me? But before we begin, I just want to let you know, do check out the courses on our website and Android app. Links are given below. All right, let's go ahead and get started. There are many theories in chemistry for covalent bonding, and we're going to study all these theories in this chapter. There's the Lewis theory, which we did in the previous video, valence bond theory, hybridization, valence shell electron pair repulsion theory, and molecular orbital theory, and so on. Again, remember, these are all for covalent bonding, where there is a sharing of electrons, not for ionic bonding, where there is transfer of electrons. Now remember, in the last video we talked about Lewis theory and the Lewis dot structure. So if you guys remember, we can draw the structure of the water molecule, for example. So in the water molecule you have these two covalent bonds, and we represented it like this with the Lewis dot structure, where you have the sharing with hydrogen, one electron is shared, and then you have these lone pairs. So this is the Lewis theory. Lewis theory was able to give us the structure of the molecule, but it was not telling us the shape of the molecule or the geometry of the molecule. So that is why more theories came which are trying to express the shape and geometry of the molecules. And in this video, we are going to look at the valence bond theory. So let's explore this valence bond theory. Before we look at the details of valence bond theory, first, let's understand what is the meaning of bonding between two atoms. To understand this, I've taken a very simple example of two hydrogen atoms here. Hydrogen atoms, you know, has one proton in the nucleus, and there is one electron here, which is a negatively charged particle, right? So this is, let's say, the nucleus of atom A, which I'm going to write Na, and this is the electron of atom A here. Similarly, in this second atom, this is the nucleus B, and it also has a negatively charged electron here, Eb. Now, if you look at these two atoms, can you tell me, are there going to be any forces here? Because we know they are charged particles, nucleus and the electrons. And what is the rule? If you have unlike charges, that is positive, negative charges, they attract each other. And like charges, positive, positive, negative, negative will repel each other. So what will be the forces here? Clearly, there's going to be an attractive force here between this electron and the nucleus, right? And within this atom also, there's going to be another attractive force. Now, if you look at the two atoms, this nucleus is going to pull this negatively charged electron. So another attractive force here. Similarly, this nucleus is going to pull that electron. So another attractive force here, right? So these are our attractive forces. So these two atoms are attracting each other, but there are some repulsive forces also, because these two negatively charged electrons, negative charge, they will repel each other. Similarly, the two positively charged nucleus, they will also repel each other because like charges repel. Now, when the atoms are far away, actually the attractive forces are stronger than the repulsive forces. That is why the two atoms are coming closer to each other, because force of attraction is more than the force of repulsion. And like this, when they keep coming close to each other, a time will come when the forces of attraction is equal to the force of repulsion over here. So in this condition, the forces of attraction is equal to the forces of repulsion. And that is where we can say that the system has become stable, right? A bond has been formed. Now, if you keep moving the atoms closer to each other, what will happen? Then the attraction will become more. Sorry, the repulsion will become more, right? Because when they keep coming close to each other, the nucleuses will repel each other more. These electron pairs will start repelling each other more. Okay, so this is important here. In this case, when they are far away, the force of attraction is greater. then the force of repulsion. And when they come close to each other at just the right distance, right, they will form a bond, because here attraction is equal to repulsion. The system is stable, and you know nature always wants to be stable. Just like we want a stable life, a stable job, similarly here this molecule or this system wants a stable life. So here the energy is lowest, and this is where a bond is formed between these two hydrogen atoms. So keep this important concepts in mind, that what is the meaning of bond, what are the forces involved between the two atoms. And here we can say the energy is the lowest. The system is most stable here. Remember, in our previous video on quantum theory and electronic configuration of atoms, we had talked about that electrons live in orbitals, right? What are these orbitals? These are basically the places where the electron is most likely to be found, where probability of finding the electrons is most. And there are different kinds of orbitals, like you have s orbital, p orbital, d orbital, f orbital, because these have different shapes, different orientations. Remember, the s orbital is spherical in shape. So your s orbital is like this ball here. Remember, it is spherical in shape. Next, you have the p orbital. P orbital is a dumbbell shaped. So as you can see here, this is the dumbbell shaped orbital, and we say the orbital along the y-axis, that is called py. The orbital along the z-axis is called pz, and this is along the x-axis, we call it px. Now x, y and z might be differently oriented in your books, right? Some books take this to be the z-axis, this to be the y, and this to be the x, so that you can check in your book. So remember, it can have these kind of three orientations, and it is dumbbell shaped. In this video, I'm going to be using the table tennis rackets to represent this p orbital, that is the dumbbell shaped. So you can imagine the p orbital. So let's look at this one, p x, or whichever one you can consider in the vertical direction, is going to look something like this, right? It will have a top part and a lower part, right? So it's going to have a top and lower part. So you can imagine it's like two table tennis rackets put together like this. And then you have the d orbital. D orbital is basically your double dumbbell shape. So you can see this is the double dumbbell shape. We won't be talking too much about d orbital. We are mainly going to focus on the s and p orbitals in this video in regards to valence bond theory. Now let's discuss the important points of the valence bond theory. What does this theory tell us? The first important point is that covalent bonds are formed by overlap of atomic orbitals. Remember, we said electrons live in these atomic orbitals where the probability of finding the electron is maximum. And so when you have this overlap of these atomic orbitals, when there is an overlap, right, that is when the covalent bonds are formed. And this happens when the atoms, they come close to each other, because the overlap cannot be there if they are very far away, right? Atoms have to come close to each other, like we had discussed earlier. So remember, when we talked about the hydrogen atom, when the hydrogen atom comes close to each other, then we are going to look at the overlap of these atomic orbitals, which the valence bond theory tells us about. So that was our first point. Now let's talk about the second point. So when do these orbitals overlap? What is the condition? The condition is the orbitals will overlap only when they are half filled and when the electrons have opposite spin. Okay, so let's discuss that. Let's say you have two orbitals. Let's say this is a 1s orbital and this is a 1s orbital. Let's say this guy has 2 electrons in it and this one has 1 electron. Remember, every orbital can have maximum 2 electrons by Pauli's exclusion principle. So if you have these two orbitals, can they overlap each other? The answer is no, because they will overlap only when it is half filled. Okay, the electrons should be half filled. So this should not be completely filled. This orbital should be half filled. Now is it okay? Now can I overlap these two orbitals? Look at the second condition. Again the answer is no, because electrons need to have opposite spin. So if you have shown one with this kind of positive spin or clockwise spin, then the other one needs to be anti-clockwise. It needs to be opposite in spin. then only the orbitals can overlap. So this is very important. The orbitals need to be half filled, as you can see here, having one electron, and they need to have opposite spins, clockwise, anti-clockwise, then only they will overlap. Clear? Now for the third point. The third point tells us that the strength of the bond depends on the amount of overlap. So this one makes sense, that if you have more overlap between the orbitals, right? So if you have greater overlap, let's say I show the orbitals like this circle here. So will this bond be stronger or this bond? Which bond do you think is going to be stronger? Definitely this bond is going to be stronger because there is more overlap. Here there is only little bit overlap. This is going to be the stronger bond. That means the bond is going to be stronger, bond length is going to be smaller, bond energy, right? Or energy required to break the bond will be greater here. So that basically is telling us that it depends on the amount of overlap. More overlap, stronger will be the bond. Clear? The valence bond theory tells us that there can be two types of overlap of the atomic orbitals. One is the head-on or axial overlap, and the second one is side-by-side, lateral or parallel overlap. So let me use these two table tennis rackets to explain you the types of these overlaps. Remember, these rackets are representing the p orbital, right? And once again, you know, the electrons are on top and below. So I'm showing half of the p orbital here. So first, let's look at the head-on or axial overlap. So when the atoms are coming close to each other, let's say along this axis, you can call this the X or Z axis, whatever convention you want to follow. So let's say they're coming along this axis and they overlap like this. They overlap like these atomic orbitals. This is your head-on or axial overlap. This is called your head-on or axial overlap. Okay. So this is the first type of overlap. Now your p orbitals could also be along this axis, for example. Okay, so they could be along this vertical or y-axis, and when they overlap like this, side by side, right? When they overlap like this, side by side, we call this the side by side or lateral or parallel overlap. So remember this, head-on means they are coming as if, you know, two cars are coming towards each other and bang, right? So this is a head-on overlap where the two atoms come close to each other or along this axis. And when the overlap is like this, it is a side by side, right? Or parallel overlap. So now let me put down these table tennis rackets and draw the p orbital for you. So let's say you have the two p orbitals like this. So if the overlap is along this axis, you can also call this the internuclear axis because the two nucleus of the atoms you can visualize lies on this. Then this is the axial or head-on overlap. Clear? And when the two p orbitals are like this, then we can say this is a side-by-side, lateral or parallel overlap. So here you can see the two axes of these orbitals are parallel to each other, right? So that is why it is called the parallel or side-by-side overlap. Clear? And once again, here I have represented these dumbbell p-shaped orbitals for you. So remember, two types of overlap of these atomic orbitals. When there is a head-on or axial overlap, we will say that a sigma bond is formed. This type of bond is called a sigma bond. And when you have a side-by-side, lateral or parallel overlap, it forms a pi bond. So we'll be discussing the details of sigma and pi bond in this video. Another important point of the valence bond theory is that the overlapping orbitals should have the same sign. Now what does this mean? Once again, let's use our table tennis rackets to understand. So what this point is telling us is that if you have two orbitals, let's say these are my two p orbitals, and if I overlap them like this, so this point of the valence bond theory is telling us that this overlapping is not possible because let's say this red represents positive sign and this black represents negative sign. So plus and minus cannot overlap. Okay, you have to use the other part. So remember, this is the p orbital has two parts. So let's say the other part is red. So only red, only positive can overlap, or only negative can overlap. Whether you do a head-on overlap, right? I was going to say head-on collision. Whether you do a head-on overlap, or if you do a parallel overlap, only this is possible. Positive. You cannot do it like this, right? And similarly, you have these, let's say the negative ends below. So then the two negatives will overlap. Are you guys getting the idea here? So let me draw the diagram also and explain. But please remember that the overlapping orbitals need to be of the same sign, whichever type of overlap you have. Clear? So what this point is telling us is that if you have two p orbitals, let's say along this axis, you can call this the x-axis if you want, or z-axis, whichever one. Let's say I'll call it the x-axis for now. So when they are overlapping, this point is telling us that when the two orbitals overlap, their plus parts should overlap. Now, what is the meaning of this sign? Why am I putting a sign here, positive, negative? Because just like, in number line, we have a sign, right? Where the numbers to the right are positive, left are negative. Same way here, when the electron is roaming around in these orbitals, we say like this side has positive sign, this one has negative. So there is a sense of direction here, right? So only these two should overlap. So if you're making these negative guys overlap, this is positive, this is negative, then another negative must overlap with this. So that is why only the negative, the same sign orbital should overlap, whether positive or negative. Clear? And these we can say is the overlap between, if I call this the px orbitals along the x-axis. So this is a px overlap here. Now can you have a px and a py or pz overlap? Let's say this is px, this is px, this is py. No, this we cannot have an overlap because the orientation is not the same, right? You want them to have the same orientation, because here the positive negative sign doesn't make sense here because the orientation is not same. So you have to take them either along like this, or so you have to take them along the x-axis or the y-axis or the z-axis, whichever way you're considering the x, y and z. Clear? So keep these important points of valence bond theory in your mind and do write it down. So remember, as we discussed, sigma bond is formed by a head-on or axial overlapping. There is a head-on overlapping or along the axis. So now let's consider the s orbital. How does the s orbital look like? Remember, we looked at the different types of atomic orbitals, and s orbital is spherical in shape. So let's say you have an overlap of two s orbitals, what I'm going to call as the ss overlap. Since it's spherical in shape, let me quickly get two balls for you. So here I've got two s orbitals for you, two spheres, right? These two balls. And so what we are going to do is, when they will overlap, what type of bond will they form? Will it only be a head-on overlap, or can you have a parallel overlap here? So if you look at this, when the two s orbitals are coming close to each other, they are going to overlap like this, right? Of course, I can't crush them and overlap them, but you can imagine this ball goes inside this goes inside that. So that is the overlap. And one interesting thing about the s orbital or the spherical shape is it is non-directional. So no matter however much I rotate it, right, it remains the same. So this is an important point, that it can have only a head-on overlap. You cannot have a parallel or a lateral overlap. A side-by-side overlap is not possible. It can only be head-on and axial overlap. So write that down. S orbitals can only give you a head-on overlapping. So if I represent the two s orbitals, which are spheres, with these two circles, we can only have this kind of head-on overlapping here. This is your overlap. So if there's only head-on overlap, it can only form sigma bond. The bond formed here will be sigma. Clear? So let's understand with the help of an example. So again, we'll take our very simple example of hydrogen, which is H2, right? And hydrogen atom, has only one electron. So hydrogen's configuration is 1s1, right? It has only one orbital, the 1s orbital having one electron. So when you have these two guys, so 1s orbital over here from one hydrogen atom, another 1s orbital here from another hydrogen atom, and let's draw their electron. So let's say this electron is like this. This electron, should I draw like this? No, remember, they must have opposite spin. So fine, we'll make it like this. And again, convention, right? You can call this clockwise or you can call this clockwise, whatever you want to do, but one is clockwise, one is anti-clockwise, right? They are having opposite spin. Where the arrow is pointing doesn't matter, right? Whether this is clockwise or not. So again, remember, this is your convention. You can call this up one as clockwise or anti-clockwise. Similarly, the other one will become the opposite. So when these two guys will overlap, right? When they will overlap, it's going to look like this. It's going to look like this, right? So this is the 1s, and this is their overlap. And so here you can say this is where your sigma bond is formed. Or we can say this is our 1s bond is formed here. And since it is a head-on overlap, right? It is head-on or axial overlapping along the axis of the two nucleus. We are clearly having a sigma bond. And sigma bond is strong. There can be lot of overlap, because greater the overlap between the atoms, the stronger will be the bond. Now what about if we have a s orbital and a p orbital? Then what type of bond will be formed? What do you guys think? So one important thing to remember, that whenever you have an SS overlap, it can form only sigma bond. Pi bond cannot be formed, right? You cannot have a pi bond here, only sigma bond. But what about if you have an S and a p orbital? What do you guys think? Let's take a look. Now what if you have an s orbital, which I'm representing with this ball here, and a p orbital represented by this table tennis racket? Okay, how will the overlap look like? So when we try to overlap these guys, it's going to be again head-on overlap, right? It's going to be a head-on overlap, right? You can think it like this, and it is going to be a sigma bond. Now you may be thinking that if I rotate this, can I get a pi bond? The answer is no. You cannot have a parallel overlap because this guy is non-directional. However you rotate it, it's going to look the same. So SP overlap, write it down, very important point, is always again going to give you a sigma bond, a head-on and axial overlapping like this. Now let's consider an example and understand it. So again, if you draw it on paper, it's going to look like this. This is your s orbital, which is spherical, and this is your dumbbell shape, which is representing with that table tennis racket. So again, you can see the bond is always, the overlap is always axial or head-on. And you can imagine this is where our electron pair lies with opposite spins. Clear? So this is your sp overlap, and remember it is forming the sigma bond. Now let's consider an example. So if we take the example of hydrogen chloride, right? Hydrogen chloride gas, it has hydrogen and chlorine atom. What is the configuration of hydrogen, guys? Hydrogen has only one electron, so it is 1s1. Chlorine has how many electrons? Atomic number 17. So you know chlorine has 17 electrons, so it's going to be 1s2, 2s2, 2p6. So there I've finished 10 electrons, 3s2, 3p5. So that's the electronic configuration of chlorine, right? So let's draw out this. For hydrogen, this is our 1s orbital, which I'm representing with this box. So you can see it is having one electron in it, and it is going to overlap with this p orbital, right? Which is not completely filled, the last 3p1. So if we draw that 3p guy, it is basically having, so this is 3p, and this is, you can say, the px, py, pz. So remember, they fill up like this. And so this last one is not completely filled. Okay, so there is going to be an overlap between 1s and the 3pz. That's what's going to overlap. Again, you can see there's a mistake here. If you guys notice, these are having the same spin. Electrons should have opposite spin. So either I can make that anti-clockwise or this one, whichever one, doesn't really matter here. So I'm going to turn this electron down, right, and make it the opposite spin. So you can see these two guys will overlap with each other. So the bond will be 1s with 3pz. The bonding is going to be between 1s and 3pz. Is that clear? Now you might be thinking, why not with the px or with the py? Again, it's a matter of convention. You can even put the single, you can make this having the single electron, right, half filled, or this one half filled, or this one. It doesn't matter. Usually in the books, they keep the last one, right? Because you label X, Y, and Z. So you're filling up from X, Y. So usually the last one is half filled. But you can follow whatever convention you want. I'm following the typical convention here, right? So 1s and the 3pz are going to overlap. So the bond is going to look something like this. Your 1s, so it will have one electron, or let me draw the electron later. And I'm going to overlap it with this 3pz orbital. So one electron here from S and this one, and this is once again your sp bond. Again, the overlapping is a lot here. In sigma bond, overlapping is more. So sigma bonds tend to be stronger. And so this is your bonding in hydrogen chloride atom. Clear? Now here you can put a sign here, positive, negative, right, if you want. But this guy doesn't have a direction or sign, right? So usually for S, we don't have it. So that's more important when you're doing the pp orbital overlap. So one interesting thing we are seeing that our s orbital, our spherical orbital, can only form sigma bonds because it is non-directional. It always does a head-on overlapping. So like you saw here, sp overlap is sigma, ss overlap is sigma. So please note this down, that s orbitals, they form sigma bonds only. So here's a summary of what we have learned about sigma bonds, that sigma bonds are formed by a head-on or an axial overlap along the axis of the nucleus, and sigma bond can be formed by a ss orbital overlap. These two sphericals, they can overlap to form your sigma bond, or a sp overlap like this. So remember here, you can see whenever s orbital is involved, whether it is with ss or sp, it forms only sigma bonds. Very, very important point. So please note it down. And as we will see, when bonds are being formed between atoms, the first bond to be formed is the sigma bond. So sigma bond is the first guy to be formed, and only one sigma. Remaining are pi bonds. Please note this down. Now here's an interesting question for you. Can you guys tell me which bond is stronger? The bond between hydrogen and fluorine in hydrogen fluoride, or hydrogen bromide? So just now we had done the example of hydrogen chloride. So we just looked at the bonding between hydrogen and chlorine, and we saw that was a 1s 3pz bonding, right? So I can write that down, that the bond between HCl, this sigma bond here formed between hydrogen and chlorine, was a 1s 3p bond, because it can be 3px, 3py, 3pz, doesn't really matter. It was a 1s 3p sigma bond. Similarly, if I ask you guys, what is the bond between HF and HBr? So come on, work out the electronic configuration, and I think you'll find out that this is a 1s, this was a 1s 3p bond, this is a 1s 2p sigma bond, because the sharing is done with the electron in the 2p orbital, and for bromine it is a 1s 4p sigma bond. So guys, if we compare HF and HBr, which is having the stronger bond? What do you guys think? The correct answer is this bond is stronger. The HF bond is stronger. Why? Why? Because this orbital is smaller, right? 2p orbital is smaller than the 4p orbital. This is in the second shell, if you think about it. This is in the fourth shell. So second shell is closer to the nucleus. So this bond will be stronger, because the orbital is smaller. Okay, so this is important to remember, that this is the smaller orbital, this is the bigger orbital, and they are both sharing with 1s. So clearly, if the orbital is larger, the bond will be weaker, and if the orbital is smaller, then the bond is definitely going to be stronger. So bond will be stronger, the bond length will be shorter, right? More energy to break the bond, whichever way they can ask you the question. Now let's look at the example of the water molecule. We have drawn the Lewis dot structure of water molecule, but how does the water molecule look like in valence bond theory? Let's discuss. So we know water contains one oxygen atom, and there are these two hydrogen atoms, right? And remember, we said the first bond formed between the atoms, right? So there's a hydrogen oxygen bond here. It should be a sigma bond. This one should also be a sigma bond. That's what we've learned. Let's check if that makes sense and how the structure looks like. So for that, let's quickly write down the electronic configuration. Hydrogen has only one electron, so it has a simple configuration of 1s1. Okay, And there are two hydrogen atoms here. So we can say this guy is one orbital like this, and another hydrogen we are going to put it here. That will also have this configuration of 1s1. Now what about the oxygen atom? Oxygen is having 8 electrons. So its configuration is going to be 1s2, 2s2, 2p4, right? 4, 6, 7, 8 electrons. So how will this 2p4 orbital look like? Or if we draw this thing, so let me draw the 2s2 will be completely filled, and this last one 2p orbital is going to look like this. It's having a px, py and pz. So let's fill in our 4 electrons over there. So we can see that these ones are half filled, so they will overlap with these. These atomic orbitals are going to overlap. Once again, we should make sure, I should have drawn it directly like this with the opposite sign, right? So it should be ready for the overlapping. So clearly you guys can see that this 1s will overlap with this thing, with this 2p, and you can call it, we can call this px, py, pz. So it will overlap with py, and another 1s is going to overlap with pz. And when s and p overlap, it's going to form sigma bond. That's what we predicted. So let's see how will our structure look like. So if you visualize the oxygen atom, it has 2 p orbitals that it's going to share with the 2 hydrogen atoms, right? So I am going to draw first let me go ahead and draw this is my pz orbital. Typically we draw the pz on the plane of the paper like this. Y is drawn vertically and x is coming out of the plane of the paper, right? Again, you can follow whatever convention you want. So this is my pz orbital, which is half filled. Okay, so I'm going to draw 1 electron over here, and then your py orbital, that is also half filled. So that's going to be perpendicular to this. So see, the diagram is looking nice. This is another p orbital which is half filled. Okay, so I've drawn our py and pz. This is our 2py, 2pz. We can write 2 here also. Okay, and that's going to be overlapping. So this is the oxygen atom. That's going to be overlapping with these 1s of the 2 hydrogen. So what will you do over here? 1s is spherical. So you're going to go ahead and bring this spherical orbital here like this. So we're going to overlap this guy with the 1s orbital of hydrogen and another 1s over here. So these are the orbitals of hydrogen atom, and let's fill in the electrons now. That will be more convenient to draw. So basically you have your 1s from the hydrogen, this is from the oxygen, this is from the hydrogen, this is from the oxygen. So you guys can see that this is the 1s, this is sharing with our 2pz over here, and this is our 2py. This is the geometry, or this is how the shape of your water molecule looks like. Are you guys getting it? Right? So along this axis, along the z-axis, again, see, this is our z-axis. A sigma bond is formed over here, and along this y-axis, this is your z-axis, this is your y-axis, another sigma bond is formed. So you have to visualize it in 3D, right? This is what's happening. This is your sp overlaps. So those are your 2 sigma bonds in the water molecule. Is it clear? Because your 1s is overlapping with the 2py, 2pz, these half-filled orbitals having electrons with opposite spin, they overlap, forming these 2 sigma bonds. These are your 2 sigma bonds formed here. Is this clear? So we looked at the example of water molecule. Now let's look at boron trifluoride. Again, we're going to apply valence bond theory and see how the bonding is done between boron and fluorine atoms in boron trifluoride. So boron trifluoride, as you can guess, there is going to be 3 single bonds between the boron and the fluorine atoms. And as we said, all these bonds should be sigma bonds, right? Because the first bond formed between atoms is sigma bonds. So let's analyze their electronic configuration and see how these bonds are formed. So boron, guys, has an atomic number of 5, right? Boron has atomic number of 5, so its electronic configuration is 1s2, 2s2, 2p1. Okay, and each of the fluorine atoms Fluorine has an atomic number of 9, so its electronic configuration is going to be 1s2, 2s2, 2p5, and there are 3 such fluorine atoms. Clear? So let's draw out the orbitals over here. So here the second shell, the 2s orbital will look like this. It's going to have 2 electrons for boron, and your 2p orbital is going to look like this with 1 electron in it, right? So this is your px, py, and pz. And here we have fluorine, and each of the fluorine atoms will be basically, if you look at the 2p orbital here, so 2p orbital is going to be looking like this. 2 completely filled, 1 half filled, right? 5 electrons in it, 1, 2, 3, 4, 5. And let me draw 3 such, because there are 3 fluorine atoms. So how will the bonding be formed? So clearly you can see this half filled will overlap with this one, and again I can give it opposite spin here, right? It should be opposite spin. Now if this one is in px, then ideally the electron should be in px, right? Because px cannot overlap with pz over here. Remember, this is px, py, and pz. So we can always adjust the electrons. So I'm going to do the complete pairing over here, and we can put the single electron with opposite spin here. So this boron and fluorine atom orbitals will overlap, right? The px and this px of the fluorine atom, there's going to be an overlap, 1 bond. So one part is easy, right? So 1 bond is done. But what about the other 2 bonds? Here there is only 1 half-filled orbital. So this is why boron trifluoride is very interesting, because to do the bonding, one of the electrons has to be pushed to the other p orbital. So this is called, it goes into an excited state, right? So we are going to excite this electron, and this electron is going to go from here to a py orbital. So it's going to look like this. So from this 2s, the electron makes a jump and goes over here. Now you can see 2 more orbitals have been half filled, right? So this one is the 2s orbital is half filled, so that can easily overlap with this one. So let's say this and this overlap, right? So you will get an sp overlap here, right? So if you look at this carefully, this is a 2s and 2s 2p overlap, 2pz or whatever you can call it, right? So this is a 2s 2p overlap. This one was a 2p 2p overlap. And the last one, py, will want to again overlap with py. Once again, we can shift the electron and make it ready for overlapping. So we can put the half filled over here, and this one can be of opposite spin. So we can say that these guys will overlap. Okay, so you can see that this py is going to overlap with this py over here, another 2p 2p overlap. So this is why boron trifluoride is very interesting, because the bonds formed here are which type? You have an sp bonding, right? A 2s, and a p bond, right? Or 2p z, whichever one you want to take. So that is one bonding, and the others are pp overlaps. Clear? The others are pp overlaps here. Now, are these sigma bonds or pi bonds? Because they are along the same axis, right? So here you can see what was overlapping. Here you had a px, let's say, and this was a py, right? And this one is an spz. So you can see that px, py, these are along the same axis. So these are clearly forming sigma bonds. So do you guys agree with me that all the bonds formed here will be sigma, and this is explained by the valence bond theory. Good. So let's review this structure together. So if you look at this sp overlap, it is a head-on overlap. So definitely a sigma bond, because s orbital can only form sigma bonds. If you look at px overlap, since the orientation is same, remember, like we had discussed with the table tennis rackets, if the orbitals are along the same axis, whether this axis, right, or you take them like this or like this, whichever way you take them, if they are along the same axis, it will be a head-on overlap, and that is another sigma bond. Same way here, p pi, py, it's going to be again a head-on overlap here, right? It will form a sigma bond. So in all these bonds, they are all sigma bonds because there is a head-on or axial overlapping. And that is what we discussed, that the first bond, remember, the first bond formed between two atoms is always a sigma bond. Only after that we form pi bonds, which we are going to discuss next. And now we are going to discuss our pi bond. So we have discussed sigma bond, and remember in pi bonding you have this kind of parallel overlap of the orbitals. Parallel or lateral or sidewise overlap. Remember, sigma bond was head-on overlap, and now we are going to discuss about our pi bond, which is this kind of sidewise overlap. Let's discuss pi bond with the simple example of the oxygen molecule. Oxygen, as you know, is O2. And the oxygen molecule has two atoms of oxygen. Each oxygen atom, let's look at its electronic configuration. It's going to be 1s2 because atomic number is 8. So 1s2, 2s2, 2p4, right? 8 electrons in it. And same for the second atom. So if we draw its this 2p4 part, so the 2p orbital is going to look like this. It's going to have a pxy, pxz. So 1, 2, 3, 4 electrons. Right? This is your px, pxy, and pz. Similarly, I'll draw for the second oxygen atom. So it's going to look like this. Okay, so this will be completely filled, and this one we are going to overlap the orbitals. So draw it with the electrons having opposite spin. Clear? So you can see that these two p orbitals are going to overlap with each other. And again, remember, py will overlap with py, pz will overlap with pz. You never have a py pz overlap or a px py. No. Y with y, z with z. But again, you can take any one, right? You can take these two could have been the x and z or y and z like I've taken. That depends on you. So in oxygen, we can clearly see these two are going to overlap. Now, how is the overlapping going to be? So how will this PP overlap look like? So first, let's talk about the PZ overlap. Z axis, as we said, is the horizontal axis. So imagine these are the two PZ orbitals, and when they overlap like this along the axis, it's an axial or a head-on overlap, as you can see. So what type of bond will be formed here, guys? This is going to be a sigma bond. Very good. So here, as you can see, there will be a sigma bond. The first bond between two atoms is going to be a sigma bond because there's going to be a head-on overlap. And what about the py orbitals? Py orbitals are perpendicular, right? They are along the y-axis. So these two orbitals, can they have a head-on overlap? Can they overlap like this? The answer is no. They have to have a side-by-side overlap because these guys have already overlapped like this, right? So these two have already, the PZs have already had their head-on overlap. So the next bond that is going to be formed is going to be a pi bond, the sidewise overlap. Remember, the second bond or the third bond is going to be a pi bond. So let's draw this out. So if I take the two PZ orbitals, so I'm going to draw them like this. Remember, dumbbell shaped. So this is one orbital and this is the second one. And these are my PZ orbitals. Okay. And here we can say, remember, plus plus will overlap. They should be of the same sign. And here when they overlap, this is where your sigma bond is formed, the head-on overlap. Okay. So this is each p orbital coming from z orbital coming from the oxygen atoms. And the y orbital is going to be like this, perpendicular to it. So it's going to look like this here and over here like this. So this is my py. Now what type of overlap these guys are going to have? They are going to have a side-by-side overlap, as we discussed. Now since there's not enough space, I can sort of turn them and try to do a side-wise overlap here. But typically we represent it like this, right? We draw lines over here to show that there is a bonding. There's a pi bond formed by this sidewise or parallel overlap between py and py. So in the oxygen molecule, remember what does the oxygen molecule look like? Oxygen molecule has a double bond, right? It has a double bond between the two oxygen atoms. One of the bonds is a sigma bond with the head-on overlap, and that is, let's say, between the PZ, right, or whatever convention you want to use. So that is between these two PZs over here, and there is a pi bond between the two PYs. So this is a p-pi bond because it is formed by the pi bond is formed by the overlap of these two p orbitals. So p orbital is very interesting. It can form a sigma bond also, as you can see here, the first bond, and the second or third bond will be of the type pi, as you can see, because there is no way these guys can do a head-on overlap, because you have to think it in 3D. So if one has done these two have formed the sigma bond, these two must form the pi bond. Clear? Next, let's look at the nitrogen molecule. Next, we are going to look at the nitrogen molecule. Nitrogen, you know, is N2, and in nitrogen molecule, you guys know that there is a triple bond. So how is this triple bond formed? Let's look at the valence bond theory here. Nitrogen atom has an atomic number of 7, so its electronic configuration is 1s2, 2s2, 2p3. See, 7 electrons here. So how does its 2p orbital look like? 2p orbital is going to look like this. So this is your px, py, pz, each having 1 electron. Each is half filled. Similarly, if I take the second nitrogen atom, again I'm going to half fill the 2p orbitals, this time with opposite spin, because we want the orbitals to overlap. So what's going to happen here? Let's take the pz orbitals. Once again, we are going to take the p orbitals along the z axis. This axis here I am taking as the z axis by convention. So these pz orbitals here are going to have a head-on overlap, because remember, the first overlap, it will try to do a head-on, right, along the axis, and this will form a sigma bond. Do you guys agree? So the first bond formed will be a sigma bond formed between these pz. Now what about the py and px? So remember, py is along the vertical axis. So here you have got the sigma bond, py orbitals are along the vertical axis, right, up and down here like this. So when they overlap, they are going to form a pi bond. It can only be a parallel overlap. And similarly, you have the px orbitals. So px orbitals, x-axis is this way, right, coming out of the plane of the paper. So imagine this is my x-axis, you can see here. So once again, the overlap is going to be parallel. It cannot be head-on. Why? Because already this bond has been formed. So we cannot change the orientation of the others. These orbitals, the y orbitals, must overlap like this, and the x orbitals have to be like this. So they are going to overlap like this. So do you guys agree that the other two bonds formed have to be parallel overlap, and these will produce pi bonds? So let's quickly go ahead and draw this out. So how will it look like? So first we'll take the two pz's. This overlap will look like this. These are your two pz's, and this is the overlap, the sharing of the electrons here, right? The overlap of the orbitals. And now if I draw the py, it's going to be perpendicular to the pz, and these guys will have a parallel overlap. So there will be formed a pi bond. So this bond formed here is the sigma bond, and these are the pi bonds. And once again, you have the x. So x is coming out of the plane. So you have to think it once again in 3D. So let's say this is your px and px coming out here. These will once again have a bond between the two, right? So you can see 1 sigma, 2 pi bonds. So if we look at the nitrogen molecule, it will have 1 sigma and 2 pi bonds. Clear? So remember, first bond is sigma, and after that pi bonds are formed. And which bond do we expect to be stronger? The sigma bond, because overlap is more. Here the overlap is less, right? It is restricted. It's a parallel overlap. Here the overlap is more. So remember, sigma bond is stronger than your pi bond. So let's summarize what we have discussed about the sigma and pi bonds. Remember, sigma bond means there is a head-on, an axial overlap. And when can sigma bonds be formed? They can be formed when there is a SS overlap, as you can see here. So this is the case 1 where you have an SS overlap. SS will form your sigma bond, or it could be SP overlap. This is case number 2. You can see S and P are having a head-on overlap like this. So this is a SP overlap that can form a sigma bond. Can a PP overlap form a sigma bond? The answer is yes. So our case number 3 is sigma bond can be formed with a PP overlap. So a PP overlap can also form a sigma bond. So I want you guys to remember SS, SP, PP, these can all form sigma bonds. And remember, that will be the first bond between two atoms. After that, there will be no more sigma bonds. The next bonds will be pi bonds. Now, when can pi bonds be formed? Pi bonds, as we discussed, can be formed by a PP overlap. So, pi bonds, which means a parallel overlap, side-by-side overlap, it can be formed by a PP bonding like this. So you can see this is a parallel overlap forming pi bonds. Any other cases where pi bonds can be formed? It can never be formed with the s orbital, that is a spherical orbital, but it could be formed with the d orbital. So basically these dumbbell shaped orbitals, they form pi bonds, just like the p orbital is dumbbell shaped and d orbital is a double dumbbell. So you could have a dd pi bond or a PD pi bond as well, okay? But we will not go into the details of that in this video. We have mainly looked at the PP overlap. But let's note it down here that pi bond can be formed one by the PP overlap, or the other cases for pi bond is it could be a DD overlap or it could be a PD overlap. So these dumbbell shaped orbitals, they have a direction, they can form pi bonds. Very, very important summary. Please note it down. Once again, I'm repeating for you. Sigma bond with SS, SP, PP. Pi bond with PP, DD and PD overlap. Is this crystal clear? Now let's try out this question. Let's say you've been asked to find the number of sigma and pi bonds in these molecules. So how will we do this? Do we really need to draw all those 3D structures, PX, PY, PZ? Let's take a look. So we'll start with the chlorine molecule. Chlorine molecule basically has a single bond, right? This is basically, remember your Lewis dot structure where these are your 2 electrons, that's your bond. So what type of bond will this be? We know the simple rule, the James Bond rule is if there is only one bond, it has to be a sigma bond. So the answer is this will simply have one sigma bond. Done. You do not have to draw all the structure, look at the electronic configuration. Let's try the next one, water. Water we've already looked at, so you guys know it already. Water is basically once again oxygen. Oxygen shares these single covalent bonds with hydrogen, and the single bond means sigma sigma. So oxygen, so the water molecule has 2 sigma bonds, one each between oxygen and hydrogen. Simple. Next one, ammonia. How does the ammonia molecule look like? Ammonia, you know, nitrogen is in the center and you have 3 hydrogens. Once again, you can easily work it out. Since the first bond between atom, right, between each a pair of atoms is going to be the sigma bond. Remember, the first bond formed between the atoms is a sigma bond. So 3 sigma bonds, done. Next one, C2H6. This is the organic compound, ethane, right? 2 carbons, 6 hydrogen. And here you know, this is the saturated hydrocarbon, right? Single bonds between carbon, and obviously carbon, hydrogen is single bonds. So the first bond formed between atoms, there's only one bond here between all the atoms that you look at. So here you can see 1, 2, 3, 4, 5, 6, 7 sigma bonds. Done. Finished. So easy. Next one, C2H4. This guy is basically ethene. There is a double bond between the carbon atoms because this is an alkene. The previous one was an alkane, and these are your hydrogen atoms. So between carbon and hydrogen, draw sigma bonds. Only one bond is there. Carbon, carbon, sigma. And the second bond, remember, that has to be the pi bond. So what does this have? 1, 2, 3, 4, 5 sigma, 1 pi. That's it. So you can write the answer based on that. 5 sigma, 1 pi. We are done. Next one here. C2H2. Who is this guy? 2 carbon, 2 hydrogen. This is ethyne. So here what will be the bonds? First bond between atoms, sigma. First bond between atoms, sigma. This one, sigma. And the next bonds, because there's a triple bond here. So first bond sigma, the other two pi bonds. So this has 1, 2, 3 sigma, 2 pi. Is the concept crystal clear? So if you're just asked for the number, you can easily find it out, remembering this important rule that the first bond formed between each pair of atoms is sigma bond, and the subsequent, right, the next bonds are pi bonds. So double bond will have 1 sigma, 1 pi, and triple bond will have 1 sigma, 2 pi. So easy, done. So remember, according to valence bond theory, we have discussed there are two types of overlapping which give rise to these two types of bonds, sigma bond and pi bond. In sigma bond, you have head-on overlap. In pi bond, you have parallel overlap. So please remember this, and let's write down the differences between sigma and pi bond. So come on, let's make this difference table. So if you write over here sigma bond versus the pi bond. So the battle of these two bonds, and you need to be the James Bond and write down the differences. So what is the first difference? The first difference is how the bond is formed, the definition of the bond, right? So remember, sigma bond is formed by head-on overlap or axial overlapping. So we can say this is axial overlapping. And in this case, pi bond is formed by parallel overlap. So axial overlap of the orbitals and parallel overlap of the orbitals, right? Second important difference. Which orbitals form the sigma bond? Do you guys remember? So as we discussed, sigma bond is formed between the SS orbitals, SS overlap, or it can be SP overlap, or it can be a PP overlap. Because the S orbital will always form sigma bond. But even the first PP bond will be a sigma bond, as we have discussed. And here in pi bonding, you can have between two p orbitals, so pp overlap. It could be a pd overlap or a dd overlap. So you can remember the dumbbell shaped orbitals, the single dumbbell or the double dumbbell, they form the pi bonds. What is the third important difference? So the third difference is about the bond strength. Which bond is stronger, sigma or pi? That's right, sigma bond is stronger because the head-on, the axial overlap is much more, right? So this can be much more, and so the bond is stronger, the bond length is smaller, energy of the bond is higher compared to this kind of a pi overlap, where the overlap is less, right? So the pi bonds are weaker compared to the sigma bonds. So here we'll write sigma bond is much stronger and the pi bond is weaker in comparison. Another important difference, as we discussed, when you have two atoms, how many sigma bonds can they form? Only one, because remember the first bond is a sigma bond. So we can say here, only one sigma bond between the atoms. But how many pi bonds can there be? More than one, right? Because after the sigma bond is formed, only pi bonds are formed, right? So pi bonds will form after the sigma, so there can be one or more pi bonds. So guys, these are the important differences between the sigma and pi bond. So please note it down and make sure these differences are crystal clear to you. And here's a homework question for you to try. You need to find the number of sigma and pi bonds in sulfuric acid. All of you know the sulfuric acid formula. It is H2SO4. And you need to apply the trick that I taught you and quickly find the number of sigma and pi bonds, and do let me know your answers by putting it in the comments below. I'm looking forward to reading your answers. So go ahead and try this homework question and put in your answers in the comments below. So friends, I hope the valence bond theory is crystal clear to you now. Remember, these table tennis rackets are our p orbitals and they can overlap like this, forming a pi bond or a sigma bond like this. And remember, this was an s orbital. You can have an SS overlap and a sp overlap as well, forming your sigma bonds. So hope valence bond theory is crystal clear to you now and you'll remember it for the rest of your lives. And do check out the full courses on our website manochaacademy.com and our Android app. I'll put the links below because we have courses on physics, chemistry, biology, maths, coding and artificial intelligence. In these courses, you're going to get live classes, interactive videos, quizzes, questions, mock tests and revision notes. So guys, what are you waiting for? Do check out the links given below and I'm sure these courses are going to help you in your exam preparation. And if you like this video, don't forget to hit the like button and share it out with your friends. And if you haven't subscribed to our YouTube channel, come on, what are you guys waiting for? Smash that subscribe button and click on the notification bell so that you don't miss out on any of our interesting videos. So stay connected with Manocha Academy and just keep on learning.
Go ahead and get started.
Camera ভেঙে দিলাম।
Oh God, আমি তোর কেন? ক্যামেরাম্যান আসছে, আমার কি অবস্থা হবে? চলো।
এটা কাটছে না তো? এই শানু, ঘুমোলে হবে? আমি জিজ্ঞেস করছি কাটছে না তো? কি করছো তুমি? দেখো ঠিক আছে, না 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 কাটবে না, কন্টিনিউ করছো না, ঠিক আছে না?